Hello, everyone. Today we are going to talk about transformations of functions, how to use transformations to graph different functions. We're going to start with vertical shifting. So our first transformation is vertical shift. What is vertical shift? Well, imagine that you are making a new function g of x out of old function f of x using addition of a number. C is a number, constant. How it can look, for example, our old function is going to be a parabola, x squared, sorry. Our new function, g of x, is going to be x squared plus 2. Let's see how the graph is going to be transformed in this case. I'm going to draw a coordinate plane. Well, guys, when you graph parabola, you know that basically you'll need to graph a little bit of this parabola, knowing how the shape looks. So what I'm going to do, guys, I'm going to graph my original parabola, this one, and I'm just going to use few points. So 0, 0 point, 1, 1, 1, 1, and well, maybe one more point like 2, 4. Remember that x2 squared is 4, so I'm going to make a nice curvy shape over here. That's my original parabola f of x. Now, what is going to happen if I take all the points over here and add 2 to them? Well, for all the same points, we are going to move every point 2 units up. For example, this point is going to move 2 units up. Well, every other point is going to do same. For example, this point is going to be over here, and this point is going to move over here. These points are going to move higher than my equation, so I'm not going to graph them. And my parabola is going to look next way. So this is called vertical shift, and this vertical shift is going to be 2 units up. What is going to happen if we subtract something like my new function g of x? Well, let me name it a different letter actually. H of x equals x squared minus 3. What is going to happen if instead of adding 2, I'm subtracting 3? Well, same way, you are going to look at all these points and move them 3 units down, because you are going to take x equals 1, for example, substitute it here, and then subtract 3 from it. So it's 1 minus 3 minus 2. So the point is going to move over here. This point 0, 0 is going to move over here. Sorry, my coordinate plane is a little bit too short. I'm going to kind of continue. That's point going to move over here. This point 3 units down. So I'm going to show that it's moving 3 units down. And like this point, for example, 3 units down over here, and this point 3 units down over here. And I'm going to graph it in orange. So that's how my new parabola is going to look. I'm going to label that we are doing 3 units down here. Well, this is called vertical shift, and vertical shift is going to be kind of applied same way to all functions, not only to parabolas. So if you have any other different function, you're just going to imagine that you grab the function and move it either up or down, depending on the number of units you're adding or subtracting. Okay. Well, next shift is going to be a horizontal shift. What is horizontal shift? Well, let me first write it down. So we are making a new function g of x using old function f of x by subtracting c units from x directly. You see the difference here? We were adding c units to the whole function. Here we are working with argument. What is going to happen? Well, let me just write down a couple of examples. So we are going to use same function, same parabola as f of x, and my g of x is going to be x minus 2 squared. How it's going to change my function. Well, let me graph first parabola. And I use a green color instead. Let me just make sure that it's thick enough. So again, my parabola is going to have the same points, 1, 1, 1, and here. Let me label the points. It's 0, 1, somewhere here 2, right? Here x, and here y. I think I forgot to label it on this, the previous one. Okay, I'm going to connect the points, build my parabola, and consider what is going to happen if I kind of subtract 2. Well, what is going to, guys, my parabola is a little bit on. Use a different color. Okay, imagine that we are looking at this point as 0, 0, right? Well, if I plug in 0 here into my new function, I'm going to get minus 2 squared, which is going to give me 4, right? If I plug in 0 here, I'm going to get over here 0. Which point I'll need to plug in here to kind of keep the value of y, to keep 0 over here? Well, the point I'll need to plug is 2. So it's kind of this point, 0, 0. If you want to keep same y, is going to move over here. 2 units to the right. And if I want to keep value 1 over here, right? How do I get 1? Well, I'll need to plug in 3 here. 3 minus 2 is 1, and 1 squared is going to give me 1. So this point is also going to move somewhere, and that's going to be point 3. And same is going to happen to all points. So all points are going to move 2 units. Let me graph. 2 units to the right. There is a very kind of simple way. I'm going to label my parabola, and this is 2 to the right, to understand which way to move. If you compare it to original function, somewhere is point 0, right? So how do you need to kind of, which x do we need to plug in over here to get it like over here 0? Well, you obviously need to plug in 2. So that means that this 0 point is going to move to 2. You can always say that's a moving of 2 units to the right, but sometimes people kind of confuse left and right. Sometimes they think that's to the left, or minuses to the left, or, just imagine that you want to find what happens to the vertex of the parabola. Now I'm going to consider some other kind of function, h of x, and here I'm going to have x plus 1. How it's going to look? Well, here to get 0 in square, I'll need to put minus 1. So my shift is going to be then over here, minus 1. And all other points are going to move 1 unit to the left. So I'm going to kind of shift them 1 unit, 1 unit, and I'm just going to connect them. Well, again, if you are not sure that you can remember like left and right motion, just remember that the idea is to watch what happens to the point which was produced by x equals to 0. X equals to 0 is producing some value of y. Well, some functions are not going to have it if they're not defined at 0, but most functions are defined at 0 and they're producing some value of y. So you want to watch where this value of y is going to move if you kind of shift x. Well, find it out at which x is going to happen, and then just shift the whole function that direction. Okay, that's about horizontal shift. Okay, now what if somebody wants to do both? So I'm going to label this 1, 2, and 3, both shift. Well, I'm going to give an example. Imagine that you have g of x equals f of x minus c, plus I cannot label the same letter here. I'm going to use a different letter, z, over here. So here we have 2 shifts. C is going to be shift to the right, and D is going to be shift up. Well, if either of them is negative, or it's going to mean that opposite direction shift. An example, my example is going to be the parabola, which is going to have like both shift sets, x plus 3 squared minus 2. Well, according to my understanding, I'm going to move my parabola 3 units to the left, this one, 3 units to the left, because, well, this minus means to the right, plus means to the left, and 2 units down, because there is a minus here. Well, let me just graph the whole thing right away. I'm going to graph original parabola, but that's going to be just for comparison. So that's my original parabola. It's y, that's x, 1 and 1. And now 3 units to the left. 1, 2, 3, 3 units, and 2 units down. 1, 2. So my vertex, this point, is going to move over here. I'm going to graph my parabola different color. So again, I'm going to watch just my few first points. That's going to be the motion. 2 units and 3 units. 3 units to the left and 2 units down. Okay, what other transformations we can have? Transformation number, well, I'm calling it 2 and 3, but that was actually 1 and 2. I'm sorry, guys. Was a little bit like off my counting, I guess. That was 1 and 2. Now, transformation number 3, reflecting. Well, there are 2 ways to reflect the function. You know that we have x-axis and y-axis, and we can reflect the function about x-axis or about y-axis. Sometimes we are going to reflect about origin also. I'm going to start with reflection. We take old function and put minus in front of it. Means that you are going to take all y values and put them with minus. Let me do the graph. I'm going to give example right away. So my g of x is going to be minus x squared. How the function is going to look? Let me scroll up. If my original function was looking like this, it was x squared. Then whenever x is equal to 1, here is going to give me y equals -1. So instead of 1, it's going to be -1. So reflection is going to be about x-axis. 0 is going to stay because it has no sign. And over here, the point is also 1. At -1 is going to be -1. So my new graph is going to look like this, -x squared. So this is reflection about x-axis. So kind of imagine that you have a mirror on x-axis and you reflect your function. Another type of reflection, g of x equals f of -x. So we put minus in front of the argument inside of the function. Well, you kind of can guess that's going to be reflection about y-axis, but let's see how it works. So example, g of x equals, I don't want to use a quadratic function because if I put minus inside of the square, it's going to give me nothing. And I'll explain later why. So the function I'm going to use is going to be a square root of -x. Looks a bit weird, but you know how the square root looks, right? Let's just grab the square root. Well, if you forgot, the square root of 0 is 0, right? The square root of 1 is 1, and the square root of 4 is 2. So x here, y here, this is 4, this is 1, it's 1, that's 2. That's my original square root, right? Now, what is going to happen when I have -x? Well, obviously, I cannot put 1 here just because I cannot extract the square root of -1. So to extract the square root of the number here, I'll need to put something negative to make it actually with minus positive. For example, I can put -1. So a square root of minus -1 is going to be equal to a square root of 1, and it equals to 1. So actually, if I use -1, I'm going to get 1. How about a square root of minus -4? Well, the square root of 4 equals 2, right? The square root of -4, that's -4, int equals 2. And you're going to see that we are going to have exactly same square root, but reflected about y-axis. Like you have a mirror on y-axis and you reflect around it. So I'm going to write down the reflection. Y-axis. Very good. Now, guys, we can, of course, combine both reflections. And if you take something and reflect it about the y-axis and then reflect it about x-axis, you are going to have reflection about origin. Normally, guys, we are not going to use it, but it's just for your information, like to understand it a little bit better. Okay, so we're done with reflection. By the way, question, why don't I consider parabola for reflection? Well, imagine that you reflect parabola about y-axis. Well, you reflect this point about y-axis, you get this point, which is already on the graph. So when you reflect parabola about y-axis, it's going to no change. Well, and you understand that if you put minus in front of x and square it, it's going to give you the same parabola. That's why I was not using parabola. Okay, our next transformation is going to be vertical stretching and shrinking. It's a little bit more complicated, but I think we can deal with it. So let me move it up, and that's going to be what? Reflection was number 3, right? That's going to be number 4. Vertical stretching and shrinking. Well, what is vertical stretching and shrinking? You make a new function multiplying your old function by a number. Depending on what number is, it's going to give you a different transformation. I'm going to start with kind of a simple example. My g of x is going to be 2x squared. So let me write down my f of x, my original function, f of x is equal to x squared parabola, and I'm multiplying it by 2. How my graph is going to look. Okay, well, I'm going to graph my parabola. 1, 2, 1. And see what is going to happen if I multiply everything by 2. So now if I plug in 0 here instead of x, I'm going to still get 0. So this point is not going to move. Let me use a red color. Okay, now if I plug x equals 1 here, it's going to be 1 squared multiplied by 2. And instead of 1 here, which it was, now it's going to be 2. If I plug in 2 here, it's going to be 4 multiplied by 2, which is going to give me 8. And this point will move actually somewhere here. That's going to be 8. And my parabola is going to look this way. I'm trying to make it looking same way. So if you look at this picture, like the number plane is made out of rubber. For us, it's going to look like you took this rubber plane and stretched it from x-axis in y direction. It's like you put both hands, like right hand and the left hand, and stretched it different directions from x-axis. And that's why it's called vertical stretching. Okay. What is going to happen if you multiply by a number less than 1 over 2x squared? Well, the point was 1. Now it's going to become 1 over 2. Let me use a different color to make sure that it's sticking up. And the point which was like 2 squared, which was 4 actually, is going to give me just 2. Well, 0 point is not going to change. All points are going to be like multiplied by 1/2. And the parabola is going to become thicker. Well, this one is going to cause shrinking. It's like you kind of pushed the rubber coordinate plane toward the x-axis along y-axis. You just pushed it and kind of squeezed it and shrinks. Generally speaking, guys, I don't think that makes sense to memorize which one is shrinking, which one is stretching. Just kind of look at the numbers and see what is going to happen to the graph. I think that's the easiest way to understand what is going to happen to the graph, okay? Okay, the next one is, oh, well, it's still green. The next one is going to be horizontal stretching and shrinking. For horizontal stretching and shrinking, we are going to, as usually, manipulate with the argument. We are going to multiply the argument by a number. Well, here, everything is going to be a little bit more complicated. And again, I don't suggest you to memorize this. You rather kind of look at the function and see how it's going to behave. My original function, for example, my original function here is going to be absolute value of x. My new function, g of x, is going to be 2 absolute values of x. Let's see how it's going to work. Well, first I graph absolute value of x. You remember that absolute value of x is making like a bisector of first quadrant and bisector of second quadrant, something like this. This is absolute value of x. Now, what is going to happen if you take all x's multiplied by 2? Well, absolute value is still going to be positive, right? Just the numbers are going to be twice bigger. So for example, the number was 1, is going to become 2. If it was 2, it's going to become 4. And the graph is going to look like this. And on this side too. Let me graph. It's supposed to be a straight line, but it's hard to draw on touch screen. So for us, it's going to look like we kind of squeezed our coordinate plane. Imagine that it's made out of rubber along x-axis toward the y-axis like this. So all points are kind of becoming closer to the axis. Though it doesn't look very like maybe, well, generally speaking, horizontal stretching and shrinking, the most visible on periodic functions like sine or cosine, but I'm not sure that everyone understands how they are going to like, how sine looks. Maybe I should give one example of a sine function. Just example, if you don't know the sine function, just skip it. Okay, but if you do know sine function, watch what is going to happen. Sine function looks like this. So that's sine of x. If you multiply argument by 2, you want to find the sine of 2x. The function is going to look like this. So it's going to look like you shrink the function toward the y-axis. But again, just to visualize this. Okay. Well, if the number here is fraction, for example, not g, like, let me make a different function. X, if it's 1 over 2x, well, everything is going to change to opposite, and I'm going to just multiply by 1 over 2. So when x is equal to 1, the result is going to be 1 over 2. When x equals to 2, the result is 1, and that's going to give me another absolute value, but looking slightly different. So this is 1 over 2x, and the green one was, this one is 2x absolute value. For us, it's going to look like we took the curve and stretched it in this direction. So the red one is a stretching in direction opposite to like x-axis, like from y-axis. Okay. Okay, guys, that's all about transformations. Normally, guys, I would kind of suggest you to memorize vertical and horizontal shifts and reflections. Stretching and shrinking is a little bit harder to memorize. So my suggestion, just look how the points are going to change. The last thing in this section is going to discuss even and odd functions. Well, really, like it's not transformations, it's just like a special property of a function. And okay, even and odd functions. I'm going to start with definition. Definition. F of x is even if for all x in domain f of negative x equals f of x. So you put minus in front of argument and you get the same function. Well, example, for example, which function is even? F of x equals x squared is an even function. Why? Because f of negative x is going to be negative x squared, which is equal to exactly x squared, which is exactly f of x. So we check this part. F of negative x equals f of x. Okay. Now, the same function or the different function is called odd if for all x in domain f of negative x equals negative f of x. So if you put negative in front of the argument, actually it's going to cause minus in front of the whole function. Example, f of x equals x cubed. If I calculate f of negative x, I'm going to have negative x cubed. If I cube minus, it's going to give me still minus, right? And I'm going to have minus by x cubed, which is minus f of x. So if I look over here and look over here, I'm going to see that if I change the sign of argument, the function is going to change the sign. Okay, so these are definitions. How the graphs are going to, or of even and odd function are going to look on the picture. Well, parabola is going to be my even function, right? Well, this is x and this is negative x. From the definition, we know that they're supposed to have same y. Means that the graph can be reflected about y-axis. It's symmetrical about y-axis. Y-axis symmetry. For odd function, I'm going to use a cubic parabola, which looks like this. I'm going to consider this point 1. X equals 1, right? Gives me y equals 1, 2, right? X equals negative 1, supposed to give me minus the value of y, right? So if negative 1 is supposed to bring me over here. So parabolas, cubic parabolas or odd functions are symmetrical about origin. My graph doesn't look very nice. Let me redo the graph. Where's my eraser? Yeah, my graph doesn't go through. I'm going to just redo the erased what I didn't want to erase actually. I'm just going to redo the graph of this cubic parabola. So x was giving me y. Now minus x is supposed to give me minus y. So again, parabolas are symmetrical about origin. Okay. Okay. Well, now guys, I want to give you some self exercises and ask you to try them for a little bit of time and then I'm going to solve them. So self work. Number 1, graph Well, in all cases, I'm asking you to graph using transformations. Here, guys, I give you two transformations at once, so be careful. Number two, graph. Here we have stretching and reflection. Number three, graph. And here we have kind of combination of several transformations. Number four, f of x. I'm giving you some function f of x as a graph. So that's my graph of f of x, given as a graph. I want you to graph g of x equals f of 2x. Well, this is horizontal stretching or shrinking. And the last question, number 5, I'm asking either function is even or odd or neither. F of x equals x squared plus absolute value of x. It's going to be a, and b of x equals, well, why don't I use a different letter for this, for the function g of x equals x plus 1 over x. Well, I'm not going to wait 5 or 10 minutes until everyone solves it. I'm going to count to 5, and you always can stop my video and continue it after you solve everything, okay? So I'm going to count to 1, 2, 3, 4, 5, and I'm going to start solving. Okay, solutions. Well, for the first problem, that's going to be, let me write it down, x plus 5 squared plus 1. What we have? Well, here we have 5 units to the left, right? Normally when it's minus, it's to the right. When it's plus, it's to the left. And 1 unit up. 1 unit up. Okay. I'm going to graph actually original parabola to stick to something. And then 5 units to the left. 1, 2, 3, 4, 5, and 1 unit up over here. And the graph a similar parabola. Well, my parabola definitely not too wide. Okay. Well, I think I'll need to continue my x-axis. Label everything with numbers. This is -5, and this is 1, right? That's how the vertex is going to be moved. So 5 units and then 1 unit. Okay, so my first graph is done. Let me move to my second graph. My second graph is -5 square roots of x. Well, guys, what transformations I'm going to do here? Well, first I'm going to apply 5. 5 is a vertical stretch. So 5 vertical stretch. -1 minus reflection about x-axis. Well, let's see. So of course I'm going to start with graphing my standard square root. Square root 1, 4, 2, 1, 0, y, x. That's my standard function. Now let me use a green color. So I'm going to stretch it 5 units up. What does it mean? Well, it was 1 here. Now it's going to be 2, 3, 4, 5. Actually, the point is going to be up over here. Okay. What should I do next? Well, next is reflection about x-axis. Reflection about x-axis means that that's going to be That's going to be -5 here. Well, the point which was 2 is going to be kind of -10. So that's -5, 6, 7, 8, 9, 10. I'm going to graph one more point here. I did not do it for the green one because I have no space there. That's how my graph is going to look. So this is -5 square roots of x. This one is just the square root of x. So first I stretched it up, like, and I reflected it. Okay, next one, number 3. Number 3 is more complicated because I use multiple transformations. We need to guess which ones I did. Well, guys, first, I'm going to write it down a little bit differently. I'm going to put the square root first. And then +2. I just changed the terms here. Now, from this formula, I'm going to see that I have transformation 1 unit to the left, right? My minus is going to tell me reflect about x-axis. And my +2 is going to tell me 2 units up. Well, what I'm going to do, guys, I'm going to do first reflection, and then I'm going to do this shift, okay? So I have a square root, that's just a square root, and I'm going to reflect it to make it a minus, use a green color. Minus square root of x. So I use reflection first. Now I'm going to shift it 1 unit to the left and 2 units up. 1 unit to the left and 2 units up. And I'm going to use a different color. So that's how my square root is going to look. That's my 2 minus square root of x plus 1. Okay. Okay, so we're done with number 3, and let's move to number 4. Number 4, I was asking you to modify the function or graph it like function of 2x. Well, let me copy the function one more time. 1, 2, -2, 1, 2. One more time, sorry, my straight lines are not looking straight. Here x, here is going to be y. It's 2, origin, and I'm going to use a red color. So my f of x is this one, and I'm graphing g of x, which is f of 2x. That's my goal, right? Well, I see that I'm going to have a horizontal shrinking. So for example, the point where x was equal to 2 was giving me the value 0, right? For this function. If I plug in 2, that's 0. I'm going to write it down. F of 2 equals 0. What is going to happen to this point if I plug in 2x? Well, what is supposed to be x to give me 2 here? X is supposed to be equal to 1, right? So g of 1 equals f of 2 and equals to 0. So, which means that this point is going to move over here. How about a point 0? Point 0 was giving me 1, right? If I plug in 0 here, it's still going to be 0, right? So this point is not going to move. And this point, -2, was giving me, I'm going to write down f of -2 was equal to 0. So what is supposed to be argument here to give me actually f of -2? Let's look back. 2 and x. To get -2, I'll need -1 here, right? So that's going to give me the point here, and my red graph is going to look like this. Again, hard to draw straight lines without touching the screen. Okay, that's my new function. Well, in red, I'm going to maybe label it over here. And my last question was asking even or odd For last question, what I'm going to do, guys, to check my question A, I'm going to calculate f of minus x. So I'm going to put minus x everywhere instead of x. Was x here and x here, I put minus x. What is going to happen when I square x with minus? Nothing. Absolute value of minus x is still the same absolute value of x, right? Because absolute value eliminates minus. So I get the same function. When function of minus x equals to the function of x, the function is even. B, g of x was equal x plus 1 over x. So g of minus x is going to be minus x instead of x plus 1 over minus x. I'm going to take this minus outside of parentheses, and this minus jumps here and can be taken outside of parentheses too. And now I see that in parentheses, I have exactly my function g of x. So g of minus x equals minus g of x. So the function is odd by definition. And I think that's all for today's lecture. Please do the homework, and I'm going to tell you that that's all.